on assertions. There are this Doulos is the same company which hosts the PDA playground, and so they have provided a quick and useful way of understanding assertions, right? So the immediate assertions is what we already considered. So there the syntax is assert followed by some property like this A equal to B. So we took the example earlier of the decoder, right? If more than one line of the decoder is on, or if none of them is on, there is a problem, right? So we were using the count ones property. We were counting the number of ones in the outputs of the decoder, and if that is not equal to one, we were saying that there is something wrong. So we should assert that dollar count ones of decoder output should be exactly equal to one. Okay. So this is a syntax assert some property, and if it is true, then say all is good. Otherwise, you could also say something is wrong. So you can use else. And the concurrent assertions are a little bit more complex. And like I was showing you earlier, system Verilog has a lot of different syntax, a lot of different ways to say, these concurrent. So here are some examples. See, if you are using a memory, maybe you don't want both read and write signals to be ever asserted together. See that you can try to write a concurrent, assertion for that, or a request should be followed by an acknowledge, and that acknowledge should come within, let us say, 2 clock cycles or 3 clock cycles or something like that. So when you want to write such assertions, you have to add the word property. Assert a property that read and write do not occur together. And usually properties are checked at certain points, right? For example, you could check it every clock. Okay, see, this means at every positive edge of the clock, check the following. Okay, whenever request becomes high, okay, it implies that after 1 or 2 units of time. So this pound sign should be interpreted as after. So if request were to go high or become true, then it implies that within 1 or 2 cycles, acknowledge will also become high. So this is called as a sequence expression. So this is an implication operator. It implies. Okay, if this is high, it implies that. Okay. So this is an implication operator. So this assertion checks that whenever request becomes high, that means you are requesting for some service. Usually within 2 clock cycles, your request will be acknowledged. The request may not be granted within 2 cycles, but at least it will be acknowledged within 2 cycles. Okay. So he has gone into more of these, what are the implications and things like that. So there are two types of implications. One is called as, by the way, this is known as an antecedent sequence expression, and this is known as the consequent sequence expression. That means if this sequence becomes, if this sequence happens, then that implies that this sequence will also occur. Okay. And these are evaluated in the same clock tick. Okay. They are evaluated in the same clock. Whereas if you write something like this, then it will be one clock cycle later. So this is known as a non-overlap implication. So if you write like this, then S1 and S2 are checked in the same clock, or either S1 and S2 are evaluated in the same clock. Whereas if you want S2 to be evaluated one clock cycle later, then you have to do it like this. And Verilog gives you an elaborate way to write properties. Okay, you can say a property and give a name to the property, and you can say what it means. Both read and write should not be high together, right? And then later you can say assert property, not read and write. That is the name of this property. Okay. So you could also write a sequence. Okay. So it's very verbose. Sequence request. Then that has this request. Sequence acknowledge has this thing, right? And then we can club them together and say this sequence implies this sequence. Okay. This is the same thing that we wrote earlier. Okay. This is identical to this. Okay. These two examples are being explained again using this syntax called property and sequence. So, mm, yeah, the fact that the sequence must be evaluated during the positive edge of the clock can be mentioned here itself. You can say that whenever the clock goes from 0 to 1, check that this property is true, right? So a clock for a property can be specified explicitly in the sequence, or it can be inside the property. So here you can put that, please evaluate this for every, or you can do it at the time of assertion. When you write assert property, there also you are allowed to write this. So there are three ways, okay, and you could also write, you know, uh, you can also write an always state. So there are many ways at which, by which you can specify that. Okay. So let me take a small example. Okay, I think that may be more useful. So I have just created one, and I will show it to you. So here is a module called request acknowledge checker. Okay, it's the same exercise that is given in Doulos. I mean, the same example that we just went through. So this is a module that checks if that property is true or not. So it takes as input the clock, the request, and the acknowledge. And we have written a property called Act3, which says whenever the clock goes from 0 to 1, verify that if request has gone high, then within 1 to 3 clock cycles, acknowledge also goes high. Okay. So this is the implication operator. So once we define the property, we can say assert this property. Otherwise, if this property doesn't hold true, then you can give this error. test it out, we can create some simple waveforms, right? So we have declared a clock and a request and an acknowledge. Okay. All are initially set to 0. Then we tie these signals to that module that we wrote earlier, which is a request acknowledge checker. And then there is a this always block creates a clock. It creates a clock which toggles every 5 units of time. And here we are doing the initial block. So at time 10, the request is going high. So if you plot the waveform, initially request was 0. Later at time 10, request went high. And then at time 20, request became 0. The acknowledge went high at 30 units of time. And acknowledge became 0 after 40 units of time. And we are finishing the simulation after 10 units. So $finish means finish the simulation. So if you plot this waveform, so what is happening is this test bench, okay, here time is 0. Okay, so at time 0, REQ was 0. Then clock was 0. And then ACK was 0. So all these were 0. We are using this to just send these signals so that this guy can check the property. Then this guy always, what he is doing is he is inverting clock every 5 minutes. So when t becomes 5, the clock went from 0 to 1. Then at t equal to 10, it came back, and 15, it again went up, and so on. So this gives a clock waveform. So this is time 5 minutes, 15 minutes, 25, 15 plus 10, 25 minutes, 35 minutes, and so on. The other initial block, remember that all these happen concurrently, right? So there's always block, this initial block, they're all happening concurrently. So when the initial block starts, time is 0. And at 10 units of time, request is becoming high. Then another 10 units of time later, it is becoming 0. And it stays like that. This is the request. The ACK, on the other hand, after the request came down, right, it took another 10 units of time. So this is where the ACK went high. So this was 10, this was 20, and the ACK goes high here. And 10 units of time later, it comes down. So what is the time elapsed between, let us say, the request going high and the clock going high? We have not had more than two clock cycles between here and here. So this is a valid situation. So this module, okay, this will not create any issues. Yeah, this will say everything looks okay. Okay. So go back and run this program. So you can see that no error came. But if we increase this acknowledge, okay, see, suppose I make this 20 units of time wait. Okay, let us see what happens. It may still be okay because we have given 1 to 3. So 20 also should be okay. So no error. But if we try to create another unit delay, then it may give an error saying this is wrong. So it says acknowledge did not go high within 3 cycles of request. So it is as though this request acknowledge checker constantly watches the two signals, request and acknowledge. And it is constantly means it does that every clock. So whenever the clock goes from 0 to 1, that is when it checks. Okay. It cannot constantly check. So every positive edge of the clock, it will come alive and make these checks. Okay, if request goes high during a positive edge of the clock, if it finds that the request is high, then it becomes alert. And next two clock cycles, next three clock cycles, it will watch out. And if the acknowledgement did not become high in those clock cycles, then it will say there is a failure of this property. But having something like this is useful during some verification. Okay. So there may be many such instances where you may want to write such properties. So there may be some communication module which is receiving some transmissions. Okay, so there is a receiver which is receiving some transmission, and maybe after receiving every packet or something like that, it will possibly want to give out a signal. Okay. Um, so that may be one way to interpret the property. That every time a packet is received, a particular signal goes high. So there may be many such, you may be able to think of more than one such example where uh, the output of a module should be asserted within a certain duration of time. If it doesn't happen, then something is wrong. Okay, maybe it's a hardware failure. Maybe the hardware has a bug. So that is what property checking is. Okay, and I have just scratched the surface. It is a very big topic. It's too heavy to discuss in a great detail here. It requires too much of. So I will not go too much into detail. Okay. So what I gave is a very simple example, right? But as you can guess, the properties can be very quite complicated. Right? Um, you can write your own checks. Okay, nothing stops you from writing your own checks. So they allow you to write your own checks as well. Okay. There are simple ones like after a request comes within 2 units of time, the acknowledge should be ready. So that is a simple built-in check. But maybe your property is more complicated than that. So if a user wants to describe a much more complex property, they can do so. So you must understand that this is not a formal verification. It's sort of when you talk about properties and so on, it may appear that this is a formal verification technique. Not really, right? It's in the simulation. So whatever test bench we have prepared, we are looking at those waveforms. And in that waveform, instead of manually going and checking the waveform and checking if acknowledgement became high within 2 clock cycles, etc., the property does that automatically. Okay. Like I have said many times before, this waveform based checking, etc., it is too complicated, right? Because the number of waveforms that you may have to look at will be very high. So it is not really possible to debug by looking at waveforms. Number two, the you know sometimes we just want to automate everything. We don't really want to sit and look at the outputs of display statements or anything like that. Okay, if that error comes, that is what we are looking for. So that is the reason why they have supported these properties. Okay. Any questions there? So you can think of other such properties. Sometimes these are called temporal properties also. Okay, temporal properties because they represent, we are looking at the waveform, etc. So temporal properties. Concurrent is another word. Concurrent properties. Here you cannot look at analog waveforms, etc. Okay, the properties cannot deal with analog, etc. They are only going to give, it's assumed that it's all digital. System Verilog is really meant for digital. Okay. Is that clear? You will have to do something else. See, if your application really wants that, okay, if you really have to check some property which has analog, etc., then you have to see how that can be done in the framework of System Verilog. Can you introduce a class, something like that? Okay. There may be a solution. The language does have certain, open sort of ports where you can go and maybe call, there is what is called as a programming language interface, right? So maybe at times you want to execute some C program inside or C++, etc. So such things are provided. When System Verilog was not had not yet been introduced, people extensively used these programming language interfaces because they found it was much easier to write a lot of these things in C. Okay, Verilog had very limited verification primitives. So they used to use programming language interfaces extensively. Today, I think the dependence on PLI is much lesser because the system Verilog supports quite a few of these things, number one. And like I mentioned, UVM, okay, that also is a one layer above Verilog. That's a layer above system Verilog. So UVM is useful if you have lot of these concurrent assertions that you want to write, right? Properties. Right? So that is when UVM may make it a little bit easier for you to write. Okay. Mhm. So I don't intend to cover UVM, but I just mentioned it to you, and you will find examples as I mentioned to you earlier in Dulos itself, the TDA playground itself. You will find some examples of system Verilog and UVM and so on. So feel free to go through this. They were all written by the engineers of Dulos. Okay, Dulos is a they provide a lot of these trainings. Okay, on system Verilog and UVM and so on. So they are a I think mostly a training company. So they have created some examples that people can go through when they are learning UVM, etc. Okay. But as you can expect, these are somewhat complex. So my advice to you is first you look at the other things. Okay. Please look at the other things that I have taught so far, right? Property checking, etc. You can do it a little bit later. Okay, don't because if you try that, the chances are that you will be very frustrated. Okay. Then another thing that uh, System Verilog provides is what is called as support for functional coverage. See, when we talk about coverage, right, there is a concept of, so I think I have a slide on this. So here is a slide on coverage. See, coverage usually means, see, suppose, you are, suppose you are campaigning for, see, nowadays I get a lot of mail from many of these people who stand for elections in IEEE or IET, etc. So we get a lot of these mails. People are trying to ask for your vote. So the number of people whom they have to reach out to is very large. Okay, there are a lot of members. And I don't know how they manage to get all the emails, etc., but they do, right? So if I have some way of finding out the emails, right, I may not get the entire database, right? The entire database may be very large, number one, and it may not be something that they can easily access. Okay, so they may have done some, I don't know how they do it, but they figured out some way of. So suppose there are 10,000 members and you are doing an email campaign that sends out the mail to about 2,000 of them, right? Then your coverage is, 20%. Another candidate may have slightly higher coverage. So ideally, we would like to get 100% coverage so that everybody who is a member knows about you and the fact that you are applying for some position and then you want your vote, they want your vote, etc. Right? In the same way, if I get a Verilog code, right, written in, so this is a design.v. So here is my design.v. In my example, usually design.v is a very one single file, but many times it is spread across many files. It may not be possible to have a single file because a lot of different people are developing these. Okay. So there may be several design files, right? And in the same way, test bench also, maybe it is possible that it is spread across a number of files. Okay. So in any case, let us consider this to be the list of test benches. And these are the designs. So if you count the number of lines in the design, let us say there are about 10,000 lines. So if I write a test bench, then does it exercise every line? For example, if there is a module, right, and that was never tested, or if there is a task which was never called, so then our coverage is slightly lower. Okay, the test bench is not able to look at all the lines. So that is called as line coverage. Another could be, can we make sure that every signal toggles from 0 to 1 and 1? That is called as toggle coverage. Then if you have branches, if then else conditions or case and things like that, is it possible for you to give inputs in such a way that every branch is taken? So you may have to write more than one test bench. You may have to write several test benches. So that is called as branch or condition coverage. That means have you been able to cover all the branches? Then there is something called as FSM coverage. So if there are several states, how many of these states were visited? Did you leave out some states altogether? In other words, the test bench could not send the finite state machine to a specific state. Okay. Maybe one way to understand this is, see, many of your faculty in colleges, right? See, there are some rules written, right? If you go and read the prospectus and things like that, there will be some rules and regulations for all students, right? A lot of times, we don't have to look at the rule book, right? Most students are, they are, they behave in a very normal way, right? And, there is a straight line. They come to the college, they take all the classes, their attendance is sufficient, they write the exams, they graduate, and things like that, right? Then there is no need for any of these rule book, etc. But the problem is many times there may be some exceptions. So some student may not have adequate attendance. Then there is a rules written somewhere, right? So if see normally when people make all those rules, right? They think of, all possible situations that could occur, and they would have found some remedy. Okay, that if this happens, we should follow this procedure and things like that. But there will be some very peculiar case for which maybe nothing is written, right? We don't know how to handle that case. The rule book itself is, not able to tell us what to do. So when somebody gives you such a rule book, right, if you can start thinking of every possible situation that could occur. What if the student, passes in, fails in the second semester but passes in the third semester? All kinds of combinations will be there, isn't it? Right? When you exercise all those, when you think of all those situations, right, there may be some place where, failure will occur. It means the rule book doesn't have a rule to handle that situation. So if if there are 100 rules, right, and you could think of enough cases to, exercise 90 of those rules, right? That means you are able to think of such cases. Then you have achieved about 90% coverage. So one way to achieve that coverage is actually through all the line coverage, toggle coverage, and so on. Right? But they don't mean much. If you think about it, line coverage, if you do, does it mean that you have achieved 100% coverage? I don't think so, right? It's easy to do line coverage. You can get 100% line coverage, but that doesn't mean much. Things will be slightly better if you get higher toggle coverage and higher. Are they good measures of verification, right? Nobody is very clear about these things, right? These are all some, things that we can get. Okay, these are metrics that if they are there, somehow makes you feel better that, we have a better coverage and all that. So that is called code coverage. So we look at the code, right? See, the thing is, the verification engineer doesn't know the code. Huh? The verification engineer doesn't have the code with him or her. They are only writing test benches. And when we do the simulations, the simulator has access to the design, and it can possibly keep some counters and check whether, the lines have been covered, signals have toggled, branches have been taken, and things like that. So at the end, it may be able to print some sort of a coverage matrix that these test benches together exposed 100% of the line, 100% line coverage was obtained, 80% toggle coverage was obtained, and things like that. So many people report these things, okay? But everybody agrees that these don't mean a lot. What is really required is functional coverage. So another similar thing, in every college, there'll be certain things like, see, if I come, let us say, as an auditor to some college, right? See, the questions that we can ask are, do you have enough equipment in the lab for a class of 40? And maybe your lab has 40 people. So we can go and verify. And are your classrooms big enough? Okay, those kind of things we can do, right? But if we have to go and ask, are you giving good education to students? That is what see, if you go to any college or any university, they will have a vision statement and a mission statement. right? So if I ask the question and say, are you, complying with your vision statement, and are you complying with your mission statement? Very hard. So functional coverage is more about, are you testing, testing the behavior. So for that reason, these guys have provided what are called as cover groups and cover points. So a very simple example is, if you have built an ALU, see, if you have a 32-bit ALU, you know very well that you cannot exercise it, thoroughly. You cannot do exhaustive testing. So you will pick random tests, or maybe you have written some directed tests. So those tests that you conducted, or the verification that you conducted, did any one of them create a overflow situation? In other words, see, every ALU will have some flags like carry flag, zero flag, overflow, right? Did the overflow flag ever get set? That is the question we want to ask. Okay. If that has not happened, then I think our functional coverage is not so good. On the other hand, these things may be good. We may have very good line coverage, toggle coverage, etc. But maybe the functional coverage is not there. Okay. So that is what. So here is. So this is the syntax for this cover groups and cover points and so on. So it's a trivial example. So take this. There is some processor. Okay, it has a 3-bit opcode, and there are possibly 8 registers, and we have the instruction may refer to. Usually every instruction, you may know that the instruction has a format, isn't it? So maybe these bits represent the opcode, and there may be instructions like add R1, R2. So we have to store the indices of these registers somewhere. And there may be other instructions where there is some, see, there may be a jump instruction, and that may require some offset and things like that. So instructions are typically encoded in certain way. Okay. So I'm assuming that there is a 3-bit opcode, and there is a 3-bit index for register 1, register 2, and there is some mode, and that's all. Right now, these are the only things that we're looking at. The mode may be the addressing mode. Maybe you have indirect addressing, direct addressing, indexed addressing. Okay. So we may have all these things. So if somebody comes and says, I have a processor and I need to verify, see, look at the number of things that can happen, right? I may have used suppose, have I used all the instructions? Okay, have I used add, subtract, etc., etc. Then within add, have I made sure that every register pair has been used? R1, R2, R1, R3. Then have I made sure that every register has been used in every mode? Okay. So the number of cases are quite high. Somebody has, let us say, written some test bench. Okay, trying to do justice to all the variety of, okay, and they are trying to be clever, and they are trying to give a small test bench which will, see, if you make a lot of tests also, it's a problem, right? It will take long time to run. So somebody has come up with a test bench. Okay. So here the test bench is, random test bench. See here, I'm doing the testing in a very simple way. I have given 50 random tests. Okay. So the instruction is, see, I have added all these things. See, these 3 bits, 7 bits, 11 bits, 3 plus 4, 7, 7 plus 4 is 11, 11 plus 3 is 14. So this should have been 14. Okay. So I have created this instruction to be a random number in this range. And I'm assigning that to all these mode, register 1, register 2. All. So people write such things, right? They come up with random instructions, a mix of all kinds of instructions in all kinds of addressing modes, etc. So that is what is going on here. Okay, this should be 13 bits, 14 bits totally. Okay, there's an error here. I want to know how well did we cover? Did we, for example, opcode? Okay. Did I get every opcode in this process? So I can create what is called as a cover group, and CG is the name for that cover group. I could have called it opcode group. So a more meaningful name would have been opcode group or something like that. And I can mention that this coverage check must be done every time the clock comes. So I can give a clock and say that whenever this goes from 0 to 1, that is when we are supposed to check. And what am I trying to measure? I am only interested in the opcode in this case. Okay, that is called the cover point. I can include other things, reg1, reg2, etc. So this is like a class. Okay. Maybe internally they use a class only to do this, but the syntax is cover group. And you can declare a copy of that, this cover group, just like, we used to define objects of a particular class. So CG instance is an instance of this cover group. And like in a group, like in a class, we have to initialize it. So in this for loop, nothing is going on except we are just creating some random data, random opcodes, random registers, etc. See, many times what could happen when you do that is maybe we'll get registers that are not even there. See, suppose I have 12 registers in my computer. The processor has 12 registers. So the register addresses are 4 bits long. But random data will not ensure that it will be um, within that 12. So if you want to do all such things, this thing won't do. You will have to think of constrained random verification, which we talked about earlier, right? But in this case, we are just being very simple. We don't want to make this very complicated. We just wrote random data. Then this part of the code uses, this particular syntax to see what was the coverage. If I do random testing, what coverage do I get? Obviously, it won't be 100%. Two reasons. One is because there are only 50 tests that we are conducting. That's one reason. And when we bring in random data, there is no guarantee that data will not be repeated, isn't it? I may get the same value multiple times because I'm generating a lot of random numbers. And it is very likely that the opcodes are repeated many, many times, and certain opcodes were never covered. So if somebody came up with a simplistic test like this, it should be possible for us to generate a coverage number and say, sorry, no, your test bench is very poor. It only gives about 30% coverage. Please go back and redo. See, that feedback is required. Without that, we are clueless, right? There are many engineers. They're all doing some verification. So if the engineer gets a feedback like this, then at least that person knows that he needs to think of better ways of generating test benches. So that is the idea of cover group. So I will leave this code here. You can enter this in that EDA playground and make it work. It's just copying that code and running it. Okay. So cover groups are used in the following way. The first thing is to define the coverage model. Okay. So usually what happens is the verification team, as I explained to you, there is usually a very large team of verification engineers. Okay. I may have mentioned to you earlier that the verification effort is usually the largest. So the number of people who are in verification is usually very large. And how do you manage such a large team, right? You may have several projects going on, and every project will have some people assigned to it for verification purpose, right? Now, once the RTL becomes available, once the design becomes available, you have to send them out to write verification test benches. And you need to have a plan, otherwise it's chaos. So usually the managers, okay, they are responsible for coming up with a verification plan. So they will go through the specification and note down what are the basic things that we need to verify, right? And this verification plan may take long time to prepare. It's not easy to prepare a verification plan because the complexity of the design may be very high. They have to read the specification thoroughly and start writing down all. See, just like I gave you the example of the rule book in a college, right? So what all will you try? See, if an auditor comes, right? What all will they want to know? What all will they want to know to see whether the college is, doing exactly the way they should be doing. This is a very common activity. You may have come across a lot of people who do all this, for ranking and things like that. People come and right. So they need to have a plan, right? They need to have all the the uh, based on this plan, they will have to write down which are the cover groups that we have to. And then first is to make sure that when we say verification environment, that includes, things like what tools are being used, what, report generation facilities do we have, waveform generation, all those things, they together constitute the verification environment. And that should not have bugs. Okay. So we have to first make sure that the verification environment is good. See, we have chosen to do this EDA playground. See, but when we tried iCarus, sometimes iCarus fails and it gives all kinds of errors. So our verification environment, we have to choose. Should we use Cadence, right? So usually when people start writing test benches, they more and more use random testing. Yeah, directed testing they will do later. Many times random tests are good. When you generate random tests, see we have looked at dollar random and U random range and so on, right? See when I repeat the test bench, right? Suppose I run this more than once. If the seed is the same, then there will be no difference. It is going to generate the same sequence of random numbers. So all random number generators use what is called as a seed. And if you want to take advantage of the see dollar random is how many bits? I think it is 32 bits or something like that. Right? So there is it can generate in the range 0 to 3 to the 2 to the power 32 minus 1. Okay, that is a very large selection of random numbers. But if I don't change the seed, it will generate the same sequence. So in my previous example, okay, if I if I'm willing to repeat this with a different seed, maybe I'll get a little bit more coverage, and then repeat it again, and then repeat it again. So if you repeat it 10 times, maybe your random data may be able to give you. Earlier it was giving 30%, but it may start giving 35%. So this is one thing that you can try. Okay? So perform multiple tests using random seeds until you feel that the total coverage is not going to change any further. Cumulative coverage means there are many engineers. Okay, there are many people working together, and they're all doing their own individual effort. So when you put it all together, what is the coverage you are getting? Maybe it is beginning to stabilize at 60% or something like that. So that is when you have to say, look, I mean, now I don't think I can use random testing any further to get any other additional value. Now you have to understand where is the gap. Meaning, this was my verification plan. Okay, and these were the cover groups. Where which is it the opcode, for example, that is not giving enough coverage, or is it the mode that is not okay like that? You have to go into uh, and then maybe you can change it. You can say, look, in this example, see the order in which I have given are mode, register one, register two, opcode. Okay. What if I reverse these two or something like that? So I'm sure the coverage will change. Okay. So people may do things like that. So they will see where the gaps are and try to do something about the gap by making changes like that. But you may still not get 100%. Maybe you will go up to 78% or something like that. Now the remaining 12% you have no other way but to write actual tests where you try to understand the functionality and say, let me write a directed test. In our testing so far, most of the time we were writing directed tests. We understood what the functionality is and we tried to write a test bench, but that is a very difficult thing to do. It takes a lot of time. Okay. See, the system is quite complicated. Whatever system on chip that people are designing is, it's huge and it has a lot of different modes of operation. So you cannot decide that, I'll only do directed tests. Okay, that will increase the number of months that you have to spend on verification. So they tried to change this by using constraint random number, constraint random testing. And hopefully the number of directed tests that you have to write will be few. Writing a directed test for a complicated design is not going to be easy. Right? So when people join as DB engineers, they will be taught to do many of these things. Okay. Those who stay for several years, they will possibly start writing verification plans and so on. So initially, they will start understanding how to use system Verilog, write random tests and things like that. Okay, so there are many aspects to verification that they will understand, and over a period of time, they will progress towards becoming managers who will write verification plans and things. Okay, this is another example of a property. Okay, I will skip this one, right? I think I mentioned to you what coverage is, right? So there is a term that you will hear called coverage closure. So there will be some number that we decide as the metric. We can't possibly get 100% coverage, right? The auditor who comes to your college for ranking and all that stuff, there is no way that guy can verify everything. Okay. So they will perform some minimal things. They only spend maybe a couple of days in your college, right? So they will have a target of how many, what is the coverage number. Okay, like maybe I want to cover 80% or 90%. Coverage closure means how to get to that number. See, maybe when we measure the coverage, it may come out to be 60%. Then we have to think of where the gaps are, analyze the reports. Okay, these verification reports are very big. Okay, and every test bench, every person who writes a test bench has their own way of writing the test bench. They may write a lot of display statements. Many of them may run into hundreds of pages. Okay, so we have to sit and understand and figure out where the coverage is low, which cover groups are giving poor coverage, which cover points are giving poor coverage. Then meetings will be held, right? And groups will, brainstorm and do all this, okay, improve whether maybe we can do a different way of constraint random testing, or they may figure out there is a bug in the constraint random testing altogether, right? And then this steps 1, 2, 3 will be repeated till the coverage is satisfied. So we say closure has occurred if we have reached that target. Otherwise, See, what can even happen is sometimes when you make changes, it may make things worse also. Okay, you try to do something, and maybe it really, it makes things worse. You are getting lower coverage than before. And remember, designs are evolving. Okay, so that is something that you need to understand. See, you can. This was your verification plan, right? This is your verification timeline. So maybe you initially took one block and verified it, and then at the end you are willing to file all the reports, right? So you will tell the designer that it failed in some of these places. Now that designer is going to fix some of those things. Okay. Now when the designer comes back with the modified design, right? Unfortunately, you have to run all the tests all over again. You may have prepared about 100 tests for this module. Only one may be failing. Let us say the 78th test bench was failing, and that is what you report. But when he makes a fix, there is no guarantee that the others will now begin to fail. The 78 may pass. Okay, 78th test bench will pass, but maybe now 56th and 48th may start failing. So you have to repeat all that work again. And so you can imagine how expensive it is, right? These verifications are also very time consuming, by the way. We are only seeing very tiny examples. But imagine, big, large blocks, right, with large number of gates. So these things take a long time, hours together. So that is the whole problem. Okay. So those tests are called regression tests. Okay. So that is called as regression testing. And people use many computers at the same time. So there will be an exclusive. They would have many dedicated computers for running these regression tests. And then once the regression test is complete, you have to look at the coverage reports. And if it is not equal to, if the coverage is not satisfactory, you have to look at all the reasons like maybe, the regression tests may have failed, no? When you schedule all these regression tests one by one, maybe something went wrong in that scheduling and maybe some tests were not run at all. See, sometimes such things occur when you are scheduling a lot of tests one after the other. For whatever reason, some of these tests may not run. For some very silly reasons, they may have failed. So you have to pour into those reports to see, and there could be some dead code in the design. So you are not getting adequate coverage. I think I mentioned that story to you, right? There was a student story which I mentioned to you, right? There were a lot of code that he was not really using at all. Okay. So that nobody can do anything. That the code is never called. Okay. So and you are trying to achieve that coverage, you will not be able to achieve because that nobody is going to execute that part of the code. And finally, maybe the test bench itself is very poorly written. Okay. So then you have to add, things like you can improve your constraint random verification and some directed tests. Okay. And also, see, in your line coverage, you may be reporting all these dead logic also, right? So you may have to discount for that, right? So all this is what a DB engineer will keep doing throughout the, uh, that is their life, right? So the ALU, as an example, if you take, there are many operations that the ALU may be capable of performing. So if you are using constrained random verification, that should ensure that all the operations are done and the data that we generate must generate all the flags. So here is an example. So you will possibly use a cover group, call it ALU cover group, and it is executed every time you clock. Okay, this is the time when you check these points. Okay, and then it allows you to create what are called as bins. Okay, so the simulators, they can classify the, the data for you. Meaning the when the test benches were run, if you were only interested in this opcode, one in the earlier example, I was just telling you whether each opcode was tested or not. Okay. I was happy if every opcode was tested. I was happy if every register was tested. But now that is not enough. Okay, we are in fact asking the tool to separately tell me how many times the add operator was done, how many times the subtract operator was done, etc. So, this is a syntax bins, right? And the name of the bin, and you can specify this op is possibly defined as a 4-bit register. So we can specify, I'm sorry, 3-bit register, and you can say, this should be 3 by the way. So 3B000 is the. So sometimes we may not be interested in only add. We may club everything together and say bins add sub op, and you can give 3B00 comma 3B001. So in which case it'll put them in the same bin, right? It also allows a default bin. If it is not any one of these, then there is a default bin. Maybe that should not happen. Okay, that may be an illegal instruction. Then you can also define uh, other cover points. Okay, this was for some other data A and B. So you can define any number of cover points as part of the cover group. It's called as a group because it has many cover points. You can also define what is called as, you may have heard about cross products, right? So if you say cross op AB, then it will check whether, let us say, A and B represent registers. Okay, like in this example that I gave, see there may be reg 1 and reg 2, right? Maybe that is a better. So imagine that these were reg 1 and reg 2. So I can say cross opcode reg 1 reg 2, meaning consider how many times the combination of add was done with R1 and R2, then add with R1 and R3. So every operation. So for example, if the registers A and B, sorry, reg 1 and reg 2, if there were 4 bits in length, meaning there are 16 registers and the register indices are, 4 bits long. And if you have 8 operations that are possible, then effectively we can have these many bins, 8 operations, 16 registers of type register 1 and 16 combinations for register 2. So 2048 bins will get created by this. So you can imagine how much time the simulation will, how expensive the simulation is. Yeah. So this is sometimes compared to, you may have seen nowadays when you have matches being televised, etc. They provide a lot of information, right? For every team, they are able to give all detailed information about which bowler, what was his track record, and how many overs has he completed. So it's called scoreboarding. Okay, this is a scoreboard that they display during the match, right? In the same way, this is like a scoreboard. It is telling you that you know you can think of this test verification as a match being conducted. So at some point, you want to know what is the score. Okay, how much you know what percentage of these coverage has been achieved, right? So that is the way this tool works. Okay, but if you try something like this in your cadence tool, etc., the only thing is I think there are other tools to report um, this in system Verilog. I don't think there is a way to display these bins, etc. Okay, so unfortunately, that they have not done. Okay, there may be another tool which can display the bins, etc. So in system Verilog, unfortunately, I'm also very curious to know if there is a way to display the bins, but I don't believe there is anything. So you'll have to manually do. So of course, we can write another task or something like that, which will maintain the scoreboard, right? But that's a lot of work, and we should not have to do that for every test bench that we write. Yeah. So they have automated that process, but I think it requires additional license, and that is not this EDA playground. I don't think at present supports that. It's a maybe it requires a different license, expensive license. So yeah, it's an alternate way to understand the same thing. See, the doctors will prescribe some nutritional requirement for all of us, right? How much protein you should take and things like that. So this is the metric. We want to achieve this metric, just like the verification has a metric, right? So the menus that are there have been prepared. So this is like the design. The design has looked at these requirements. These are the specs. Okay. And the menu is following the spec, and it has created okay, but somebody has to actually serve those meals, right? And note down, see, everybody doesn't consume everything that is served to them, right? So you have to actually see, in real time what is really happening, right? How much food was consumed of each kind. See, you can imagine how complicated that is, right? And at the end, we can give a coverage as to, for that person, this person, whether he got his daily requirement of nutrition or not, suppose you have to give a report, right? So that is what this verification is trying to achieve. Okay? So let us, we are coming to sort of towards the end of the class now, right? So I am going to end it with maybe some ideas on what people are trying to do in order to get higher coverage and so on, right? So I think a very popular topic nowadays is the use of artificial intelligence and machine learning. Okay. So anything you take, there is somebody trying to do, AI and ML for that, right? So design verification is also not very different. So a lot of people are working on. See, there is good reason for that, right? The amount of money they spend on verification is huge, right? So if a tool can help in reducing the effort in verification, it will be the companies will be very keen to do that, right? So that is the reason why there is so much of interest in applying AI and ML techniques. Okay. So currently, human beings go and analyze the coverage reports. They are the ones who check whether some tests did not run. Okay, if you take a regression report, sometimes the script fails because of some very silly reason, right? And as a result, a particular regression test was never run. So today, going through all the reports is a human thing, right? Human beings are doing it, but it is something that the AI can possibly do. And, similarly, with where the gaps are, right? Again, today human beings are the ones who look at the coverage groups and what was the targeted coverage and how much was it obtained. So this is also heavy. It's data intensive. Okay. That is why I think a lot of human beings have to get involved. But you can try using AI. And I think there are people who have proposed, and I think some companies also are doing these things, right? I think nowadays all these Cadence and Synopsys, all those companies, right? Siemens, they're all bringing AI and ML into that. Okay, and maybe it can also suggest some constraints for CRV. That is, see, writing those constraints are sometimes very tricky. Okay? When I talked about constraint random verification, you may recall that there are lots of ways to generate those constraints, right? Um, I showed you a few examples, such as um, maybe the opcode should be inside some range, right? But see, if you look at the actual instruction set of a computer, every operation, every opcode may not be associated with every register. For example, the jump instruction may not be associated with anything other than maybe there is a usually a link register or the program counter. These two are the only ones that get impacted. There is no relation between instruction and R1, R2, etc. So you may have to write more complex random constraints to handle all those complicated situations. Like if the opcode is jump, then choose these two registers. If it is add, then maybe certain modes are permitted, whereas if it is multiplication, some other. See, you go to, let us say, for the ARM instruction set. See, many of you may have used ARM architecture, right? You'll realize it's very complex. The instruction set is very complicated, right? And you'll have to go if somebody has to say that here is a risk in, I'm sorry, the ARM implementation, and you want to verify it, and you are going to do CRV, right? It won't be trivial. You can't just do simple random number generation to do. So what you saw earlier, okay, this was very crude. Okay, nobody will do it like this, right? You have to think of a better, more intelligent approach. Then they are also trying to use AI or things like test case prioritization and scheduling. See, all tests. Imagine that there are many test benches. See, there may be thousands of test benches. Right? There may be some value in doing some of them earlier, okay, because they will fail quickly. Then those are more. Then you can quickly give some feedback to the design team, right? Because these are very critical problems in the design. There is no point in verifying all kinds of things in the design and then find some very critical issues, isn't it? Right? See, that ranking team that comes to your college, they should focus on some important things, right? Not some peripheral things like, does your department have a, some, is there a, you have a way to serve tea in your committee room or something like that. See, those are all trivial things, right? Or does, do you have a way to collect attendance for faculty or something like that, right? See, those are all not so important. I think we should focus more on the bigger things, right? In the same way, the AI may be able to look at all the test benches and looking at the design characteristics. Okay? So you see, usually verification engineers don't have access to the design, okay? Because they are not. You cannot expect the verification engineer also to know design. But the AI tool may be capable of looking at the design characteristics and then prioritize certain test cases. Okay, that's an advantage. That is where AI will, sort of score over human beings, right? In companies, you don't find people who do DV also do the design or the other way around. Similarly, people who do layout, see, they don't go and do other things. Okay, that itself is very complicated. But AI tools can sort of do many things, right? And similarly, it may be able to look at history information, right? See, human beings cannot do all these things very well, right? If how many of us remember what happened, let us say that committee which came for your what is it called, that ranking. Okay, suppose the same committee visits 3 years later. Will they remember what happened in the previous one? Maybe there is a report that was written. Okay. Maybe using that report, they can again go back and ask, okay, have you, last time when we came, we made these remarks. Have you done something about it or something like that? But they may have made so many, mental notes about, not everything is written down. Okay. So when we run these reports, there may be, every regression, there is history, right? This failure occurred, that failure occurred. It's very difficult for us to look at all of that together. But AI may be able to find patterns. Okay, and say that, all of these are indicating that a specific module is the one which may be causing this or something like that. Okay. Then, like I said, which tests must be used first? This I already mentioned. Right? And what tests are likely to cover new books? See, you have reached a stage where you are seeing that the coverage is sort of converging at 78%, whereas your target was 90. Okay. So how do we come out of this? CRV alone is not going to get you very far. So presently, this is all done by senior verification experts. Okay, but they may take long time because they have to go and investigate. But that is where maybe AI tools can help. And I think they're also looking at LLMs like we are all using these LLMs nowadays, right? They may be able to create. See, when young engineers start their, you know, uh, writing of test code, etc., they don't have to remember syntax and things like that, right? You saw me struggling with syntax, right? Some semicolon is missing or some word is misspelled and all that. So that is why we take long. Okay, but maybe there is a way to use the LLMs to assist you in, maybe it parallelly looks at, see, once upon a time, editors did not even have color coding, right? It was very difficult, right, to find bugs, etc., or even syntax errors for that matter. But today, these editors are fantastic. They have all this color code. They understand that language very well. See, our what is it called? The EDA playgrounds very editor is very poor. The only thing it is giving is maybe it is color coding and highlighting the keys, keywords, right? But if you have a better tool, right, which can improve your productivity by you can just tell it, I am looking for this cover group. I don't want to know how to create the cover group, the syntax and all that, right? So maybe if you do that, the editor may be very smart, and then it can understand what your goal is, and it sort of plugs in that whatever you are trying to do. So that is where they are trying to do. That's another thing. So these are some 3 4 ways. There is also AI is also being used to achieve better closure, coverage closure. So I think I mentioned that targeted tests can be written by. It may not be able to write the tests, but at least it may be able to suggest. Okay, and I think I mentioned this point, right? It will look at the semantics of the design and the test bench, right? See, this is hard for a test a DV engineer, right? Because they will not understand the design so well. Right? It's very difficult to understand the design. See, people who work on the chip, they will not be able to understand the whole design. Right? They are only working on one small part of the part. Just like you may be a lecturer in electronics and communication department. You will not know what is happening in other departments and those things you don't know, right? You just know one little part of your work. In the same way. And waveform analysis, right? Again, image processing kind of application, right? So maybe it is possible to find certain patterns in the waveform analysis, right? Based on whatever I explained earlier, that what is it called? The sequences, concurrent assertions, right? So through waveform analysis, it may be possible to find some bugs, right? And even predict coverage closure. So there are, I think I saw at least one paper which was talking about, without executing the test code, prepare, go ahead and estimate what is the coverage closure that you are likely to get. Okay, so this is, so you can also find these papers there. I think this is possibly from MIT. So I saw one paper like that. Without executing, how can you get the coverage closure? So that may be some based on uh, some sort of a what is it called, the training based on that, what is the training called, the supervised learning. Okay, based on supervised learning, they may be able to predict the coverage close, and they may even be able to go and do root cause analysis. If something is failing, we don't know what is the reason, right? It may be the verification has a problem. I think we encountered this many times during the course. Many times the design was not the problem. The verification sometimes was having some problems, right? See, today I explained, right? See, there was a bug in my program. See, when I added up the numbers here, I made a mistake. Okay, this was supposed to be 14 here, but I made 13 here, right? So finding such a bug is going to be quite difficult, right? We may be cracking our head why we are not getting all the combinations, etc. But there is a bug here. So one of the bits will always be zero. Okay, the most significant bit will always be zero because we are only generating in the range zero. So we will be worried why we are not getting coverage and things like that. So that is the root cause. That is what is called as root cause analysis or debugging. Okay? And this may raise some ethical issues also, right? Sometimes, who knows, the root cause may be maybe a human being will be made, the scapegoat and things like that. So there are some ethical questions also that are tied to all this, right? Then finally, I think this last point we already made. They're also looking at whether assistance can be given in verification planning. So, like I mentioned, this is usually done by very senior managers, okay? People who have many years of experience in verification. They are the ones who do verification planning. But since AI can read natural language, okay, so it can read the specification which is written in natural language and maybe highlight certain key features and requirements and assist the managers in coming with a verification plan. Because many times the natural language may be so difficult to understand. Not difficult to understand, I would say subject to ambiguity. So if somebody can alert us about those ambiguities, that is like a good thing, right? So this is a slightly different model where we don't entirely replace the human guy, but he will have an assistant who is an intelligent assistant, right? Another could be use how to optimize the compute farm utilization. So when you do the verification planning, it may also involve things like meticulously figuring out the timeline and see the compute farm that the company may be using, right? See, big companies can afford to have their own compute farm, right? But smaller companies may be dependent on some cloud-based compute farm or something like, right? So planning all those things, right, and making the reservations of compute farm, even in a way, even if you have your own compute farm, there is an intense competition for that, right? There are so many people trying to do that, right? I mean, there are many chips that are being designed. So what can happen is there are times when nobody is using it, and there are times when everybody wants to use it. Okay? So maybe the AI tool can look at the current utilization of the compute farm and intelligently schedule the verification and things like that. So the whole reason why AI seems attractive to everybody is because it can see about 70% they say of the total design cycle time is spent towards verification. So if it can bring it down even to 60%, people are quite happy, right? So they are trying going after reduction of verification cycle time, and also maybe it can help very difficult and mundane tasks. See, there are some very this constraint random verification, etc. See, it's very after some time it will become very boring, right? You just keep trying different seeds, etc. There is no, it's very boring kind of a work. So maybe some of this can be offloaded to AI, and maybe it also helps you to improve the quality. Maybe you are achieving 82% coverage. Maybe with this you may be able to achieve higher coverage. But these are not so easy, right? This is there are a lot of challenges because all these AI models are highly data driven, right? You need good data to train those things, right? So though everybody is jumping and saying we have AI, etc., I think only time will tell whether some things will be good. Like I told you about the editor, right? See this. Uh, See this kind of stuff is good, right? I would also like to do that, right? I would like a better editor that can help me write a better code quickly, right? But if you are talking about going through the verification plan and suggesting alternates, etc., you need data, right? So companies should be willing to share that kind of data with EDA companies. Remember, the EDA tools are created by other companies, and design is done in other companies, right? So the data is actually with the companies, right? So you can't go touch the data. You can't start collecting all that data and try to. That will be a violation. And not only that, you cannot just train once and for all and say that's it, right? Constantly things are changing, and so you have to spend a lot of money in trying to, continuously train those AI models. And if there could be biases in the data, see, which data are you going to look at, right? Not all teams are the same, right? So maybe the data that you got was not the best. So that may have created some bias in the data. So you may be making wrong or somewhat not so intelligent suggestions. Right? And then another thing I think is when if an AI tool were to come up with a suggestion or it is finding some issue in the verification plan or something like that, or if it is finding that there is a particular failure or something like that, a human engineer will be able to explain the reason why he or she thinks there is a reason, right? Whereas the AI tool, at least it should be able to explain this analysis. You may have also noticed, right, when you use these AI tools, there is no guarantee that it is, whatever it is saying is correct. Okay, we don't trust it with very. It's okay for small things, but many times we don't want to trust it with. Right. In the same way, it will take time for them to build trust. And finally, it has to integrate with tools, right? That is what they are all trying. So all the companies, Cadence, Synopsys, if you go to their websites, you will see they're all trying to put machine learning and AI into their tools, right? So yeah, so that is, I think, all I had in mind for your class, right? So Professor Vinit Sahula, it is around 4:30.
Sir.
If there are any questions, I'll be more than happy to take, right? Otherwise, we are done. Any questions before we break? I'll send whatever code was generated today, I will send. And it'd be great if you can attempt those exercises that I have been giving, right? You have to practice. There is no point in just attending a class unless you are going to follow up with some exercises and so on. And you will find a good number of, there's plenty of literature. Okay? There is plenty of literature. You have to, and the good thing is the tools are like, at least Icarus system Verilog is free for you. And even that UVM is, free, but I didn't discuss that. I didn't discuss UVM, but you are welcome to dig into it and try to understand it on your own. Any questions before we conclude? Is it really possible to have such tools? I think so. Yeah, they are quite serious about all this. Yeah. See, did you at some point imagine that something like Chat GPT is possible? No, right? At that time, it looked, if somebody had said that such a tool will come in the future, uh, maybe people would not have believed it, right? But it's possible. There may be ethical issues and biases. Yeah, yeah, you are right. I mean, that ethical issues continue even for Chat GPT and all, right? So, see, somebody may take whatever chat. Why do you think that that OpenAI, that Sam Altman, why do you think he repeats that? Don't take it seriously. Okay, it may occasionally not give correct answers, so you have to have your, you know, you have to take whatever it says with a pinch of salt, right? That is the reason why keeps saying that, because somebody may start using it as a, somebody may trust it, right? So much that they go off in the wrong direction altogether. Right? Yeah, absolutely, that is a reality. They don't come with any promises. So that is why all the what appeals to me is the things like intelligent editor for system Verilog, right? That's a good addition. Like Python. See, when you write Python code, it's very nice. The experience is very nice because um, they are so intelligent, right? You realize that, right? But I don't see anything like that in, or maybe I don't have it. Maybe I can't blame. I only seen the ones which are available for free. But I have not come across. Frankly, even in the industry, people are using ordinary editors. They are not using any. I have not seen any special editor for Verilog or System Verilog and things like. What was the other question? Something somebody asked. Yeah, I mean, how things will be a few years from now, it's very difficult to say. Okay? There is plenty of investments being made, right? And people are seriously investigating, these possibilities, right? Huge amount of investments have been made. A lot of startup companies. So you will see they will all be used, definitely. Sure. Anything else? So you all have to become better than AI. Okay? And you have to understand where the AI has difficulties, and you have to secure yourself by doing better than AI. That is a challenge that we all face. It's not just you or me or everybody faces. Any other questions? Any other comments? AI. Is it necessary to learn AI ML in today's time for a design verification? No, I don't think so. It may be an advantage for slightly experienced guy, but if you are an entry level DV engineer, at present, I don't think people are going to insist. As a matter of fact, I think the tools are just beginning to, come up, the synopsis, cadence, etc. They are now beginning to integrate AI. So I don't think anybody will expect that you should have AI and ML knowledge. Mm. And I don't know whether AI and ML knowledge will help you in using those tools in any better way. Okay. See, I am using ChatGPT, but I don't know how that it works internally. Right? I don't care. Right? I only am a user. I only thing is I should be watchful when it is bluffing. Okay, a lot of times it just bluffs something and gives some vague answers, right? So that is what we have to watch out for. Will AI take away verification jobs? Possibly, yeah. I mean, maybe. See, that is the reason why there is so much investment, right? Think about it. Is that 70% cycle time that I mentioned, right? Uh, so you see, it also means that a very large design verification team, right? So expenditure is something that definitely bothers people, right? So I won't be surprised. So I can't say how many. I can't say how many, but I can definitely say that any others. A lot of papers are becoming available, so you are welcome to look at those, right? So usually, I think these are published. See, you can look at the Design Automation Conference. Okay, that is one source. Then there is a conference called DVCon. Okay, that is held every year, and I think they hold it across different parts of the world. I think in India also they hold it. But maybe you can look at DVCon to see. Then the companies hold their own conferences. Like every company, all the three big companies like Siemens and Cadence and Synopsys, they hold their annual conference. They also do it across the world. So at least Synopsys will hold one in India, Europe, US, right? And possibly in China also. So they hold it in different places. And you can look at, and these are usually available for free. Okay. So they would love to have you go and look at their proceedings. Right? On the other hand, IEEE conferences, etc., you will have to buy the proceedings, right? Whereas these user conferences like Synopsys User Conference or Cadence, I think it's called SNUG, Synopsys User Group. So SNUG is a conference that is held every year. Similarly, Cadence Live, you can look at those. Many times they also record their keynote talks and things like that, right? So you are welcome to look at those, right? And if you are interested in serious technical papers on this topic, you should look at. I think DBCon is definitely a good one. Then in addition to that, IEEE transactions on CAD may be a good place to look at. And there may be so many others that I don't follow. Okay. Professor Vinit Sahula, anything that
Yes, sir.
so if you feel I don't see any more questions coming, but
Sir.
so shall we close?
Yes, sir.
Okay.
Uh, this is the final talk, sir.
Yeah, yeah. I'm closing today. Yeah.
Yes.
We finished, no? We
Uh,
finished
yes, sir.
the required number of.
Sir. So we'll just take 5 more minutes, sir, with you on that way. Thank you.
Sure, sure.
So I think, like every good thing has to come to end. This program is also now being completed, but only to get us initiated into this the domain where the requirements are uh, quite versatile and demanding. I think it's time to thank Ravi Kumar sir. We are grateful to him for having consented to engage us for so long, and he is the sole instructor for this whole program. He has opened up so many dimensions to us to look at those things. Like he very easily explained the language constructs, following language manuals, and still kept us interested in the whole kind of thread for verification learning that way. He has also exposed us to many diverse offshoots of this verification, like assertion-based verification, formula verification, and somewhat for testing concerns about that part. I think we are all thankful. I think we would like to join me in thanking him gratefully for the more than 40 hours, the way he has worked hard, put in efforts, and of course, these are 40 hours visible to us. Before that, he would have devoted much of time in designing the pedagogy to convey all this to us. We convey our heartfelt thanks to you, sir. Thank you very much.
Yeah, yeah. Thank you, Vineet, and I thank you all for the
Yes, sir.
all the arrangements that you had to make. It's
It's
not
an
easy
honor,
to
sir.
do all this, right?
No, sir. The
And
participants are very
you
interested.
and your team have worked very hard to make this happen. Thank you. And also, I
Yes,
think
sir.
I thank the participants for
Yeah.
being there. Yeah. And
So if you allow, sir, we can ask participants to express themselves just for 5 to 10 minutes, if you that way.
yeah, yeah. No, I have no problem.
Yeah. So this platform is open to participants. You can take one by one turn and express your feelings and put some of your suggestions about the topic, the timing, if anything we can do for improving our organizational efforts, you are welcome. You can please take up your turn one by one and express yourself. You are welcome now. The platform is open to you, all the participants. Yeah, Prashant, if you want, you can unmute yourself and express. Mr. Prashant Patwardhan.
You can
Kusumlata.
introduce yourself. I'm particularly interested in listening to the faculty members.
Yeah. Dr. Kusum. So Dr. Kusum is good friends of ours. She is an alumni IT for
Oh,
long,
okay.
and she is head of the ECE department there.
Yeah, yeah. So I'm curious to know whether they are planning to integrate some of this into the curriculum that they are offering.
Good evening, sir. Am I
Yeah, good
audible?
evening.
Sir, this
Yeah,
question
good
Lata
evening.
is already, yes, sir, introduced by Professor Saula. I am working as professor in LNM IIT Jaipur itself. And actually teach this course, which is
Oh, nice, nice.
designed for testability, right? And I'm a alumni of IISc Bangalore, so that's where I learned about this course from Professor Viren Singh, and Dr. Subir Roy is my co-guide during those days. He taught verification, and Professor Viren Singh, he taught testing part of it.
Yes, yes, yes.
So that is how I was introduced to this domain. And the continuation of that, there are a lot of things which comes up. And with that, when I attend such FDPs and such events, which are so rigorous, which comes from the experienced people like you, I keep attending, and it is always insightful and like very refreshing. And there are a lot of things which I'm still learning. Like this FDP, I learned a lot of things again, which I am going to include in my class sessions also. Thank you so much, Ravi sir. It helped me a lot because we are starting our semester in August, and I'll be teaching design for testability course where I'll be taking a lot of things from your lectures. Thank you so much once again.
Thank you, Professor Kusum Lata. Okay. Any other faculty members?
Yeah, Miss Poonam, please go ahead. Not audible, Miss Kusum. Miss Poonam. Okay, we'll try. I think the rights for unmuting yourself are with you only, but we'll try. Geeta, can we unmute Miss Poonam Kadam?
Yes, sir. Request has been sent, I think. I'm not able to unmute, but I have sent a request to her. Let me check once.
Yeah. Yeah, anybody else? Please.
Hello, sir. I am Dr. Ajay Mathew from Central Institute of Technology, Kokrajhar. I teach in Electronics and Engineering department. Right now, I am outside, but I would like to say thank you to for all the lectures that you have delivered. I mean, this is my first introduction into verification, though I heard about it. I know Verilog. I teach Verilog in the VLSI course, but through these lectures, I am inspired to integrate some of these verification experiments also into the VLSI lab. So thank you very much, sir.
Very good, very good. I'm happy to know that some of you are planning to consider integrating some of this into whatever you are teaching. So that would help the students, right? Very good. So there is a big gap. See, we talk about the gap, right? The curriculum that is taught in the universities and what the industries look for. I hope you got an idea of what that gap is by whatever I have covered today. Is very, I would say it scratches the surface, right? There is a lot more that one has to learn. and the tools are very complex, right? I have not gone into all the aspects of the tools. Mm, So I hope you get at least you got a glimpse, right, of the complexity of the problem and so on, right? So we need to work hard on making our courses like digital design, right? And maybe even the DFT course that is there, right? I don't think many universities have a course on verification. Um, Many people use Verilog as part of the design class, right? But unfortunately, the coverage may not be so high, right? Because they have to teach the digital design concepts and the language. It's very difficult to do it in one course, right? So as a result, many times students come with a very superficial knowledge, right? So I don't have a very good solution as to how to change that, but the fact remains that something has to be done, right? So we have to see what can be reduced, right? Maybe there are some things that we are teaching that are either not necessary or may not be, we don't have to emphasize them so much. So we have to look at that and see whether we can strengthen certain areas.
Sir, I also would like to contact you further. Is that possible, sir?
Yeah, sure. Why not?
So, okay, sir. I mean, especially to take some suggestions for giving projects for the students.
Yeah,
Thank you, sir.
sure. I think some of you were very actively participating. That really helps. Without such active participation, it can be very boring, right? So I think you, Dave, and Lakhan Yadav, and some of you were constantly participating. That is also very important. So Vineet, maybe I think Dr. Poonam is unable to unmute herself, right? So it's okay. I think.
Yes.
Yeah.
We wait for anybody else want to express herself, himself. Right. So I have request to all of you participants. Please take up assignments in the canvas, and the assignment marks will contribute to the overall performance, where minimum attendance, minimum performance is taken into account for decision to award you a certificate. We are thankful to you for joining the program, because this program is made up for you only. We see ourselves at Academy, ICT Academy, as a humble facilitators, bringing you the best experts in any given field, and it is up to you to join and participate and take part. So thanks to you for being patient and be very good and keen listeners and learners. Lakan, if you want, you can unmute yourself. You want to say something? So like every good thing has to come to an end, and it is now our turn to take ahead what we have learned pedagogically and technically, and imbibe that into our own teaching at our own place, and initiate some good courses that way. So thank you all participants. And
Thank
thanks
you,
again to you,
Vineet.
sir. Thanks again to you, sir. Thank you very much for
Thank you,
being there.
guys.
Thank you.
Thank you so much.
Thank you, Geeta. Thank you, Ramesh, Deepesh, and Manish. Thank you all. Thank you very much.
Bye bye.
I'm also here. I'm also thankful to my director, Professor N.P. Padi sir, and my whole establishment in my institute for facilitating us to do such kind of programs. So happy learning in future. All the best for your future endeavors. Goodbye and have a nice day. Thank you very much.
Bye-bye.